So each species that we examined in the previous screencast has a single pi system, but more than one pi system can appear in the same species. And so we have an example shown here. One pi system is the terminal carbon-carbon bond on the left of the species. And then kind of here, and then the other pi system involves the C plus and the carbon-carbon double bond on the right. Now, effectively, these two pi systems are isolated from each other. So this is called an isolated system. And the tetrahedral carbons that appear between the two pi systems are the reason why. So it's these tetrahedral carbons that appear between the pi systems. Tetrahedral carbons aren't going to have a valence pi orbital or p orbital contribution, so conjugation is distributed on going from one pi system, disrupted on going from one pi system to another. So let's put some words to this. Tetrahedral carbons disrupt conjugation. So pi systems appearing on either side of a tetrahedral carbon are effectively isolated from each other. Now, because conjugation increases stability, the outcomes of chemical reactions can vary depending on whether pi systems are conjugated or isolated. So let's look at this example. We have two different alkene products that can be produced from the E2 reaction shown here. The new double bond is conjugated in one product and isolated here in the other. So the product where the new bond is conjugated is more stable, and so that makes it the major product. The quantitative difference in stability between conjugated double bonds and isolated double bonds can be determined from the heats of hydrogenation. Now, I really believe that's, again, outside the scope of this course and more fit for something like physical chemistry. But if you're interested in that, you're more than welcome to read on your own, and that would be section 14.3 in your book. Now, the species shown here has two separate pi systems, right? And even though it has no tetrahedral carbons. So one pi system has 4 pi electrons that are delocalized over 5 carbons. And then the other pi system has an isolated pi bond consisting of 2 pi electrons. When we look at this, right, and so here are the two that are isolated. So we've got a pi system where they're delocalized, right? But these two here that make up that double bond, because we started with a triple bond, but here it's a double bond, those are isolated from all the rest. Only one p orbital, which is shown here in blue, from each of the sp hybridized atoms can be parallel. And so they're the only ones that can be conjugated. The other p orbital, which is shown here in green, are perpendicular, and so they overlap with each other and they form that separate pi bond. And so here's kind of the take-home message, which I typed out for you. At most, one pi bond from a given triple bond can contribute to a pi system. So when we're talking about a pi system, only one pair of pi electrons from a triple bond is going to contribute. Now, let's look at the allyl anion. In the Lewis structure of the anneal anion, a lone pair of electrons and a -1 formal charge appears on one carbon, and right here, and the double bond here connects the other two carbons. And so we have two resonance structures. In each resonance structure, the negatively charged carbon has 4 electron groups, okay? And that in a lone, so 3 single bonds, right, in a lone pair, and that suggests a tetrahedral electron geometry and sp3 hybridization. Notice the resonance hybrid shows that all 3 carbons are involved in the electron delocalization. So each carbon must contribute then a valence p orbital in the same pi system, and that only really occurs if all 3 carbons are sp2 hybridized. Now, because converting from one resonance structure in the allyl anion to the other requires moving 4 electrons, we can see that the allyl anion's pi system also has 4 electrons here. In the acetylide enolate ion, which is shown here, right? This is an example where the atom involved in resonance, which is specifically oxygen, has more than one lone pair of electrons. Now, both the carbon and the oxygen are involved in resonance, so each of these atoms have to contribute a valence p orbital to be able to use the same pi system. And so what we see here is that all 3 atoms are sp2 hybridized. Like the allyl anion, the acetylide enolate anion has 4 pi electrons in its pi system, right? These 2 are moving here, and these 2 are moving here, and that gives us 4. The electron movement indicates that the oxygen contributes 1 lone pair of electrons to the acetylide enolate anion's pi system. And so the 2 other lone pairs shown here are perpendicular, and that means they're going to be isolated from the pi system. And so we can make an even more general rule that an atom can contribute at most 1 lone pair of electrons to a particular pi system. So that's a more general rule as we're looking at these pi systems. Now, so far, all of the pi systems we've really talked about have been acyclic. However, resonance can also occur where all the atoms of a ring are involved. And as I mentioned on the very first slide, benzene's a really common example of this. Benzene consists of alternating double and single bonds, right? And so we can draw 2 resonance structures shown here. Now, because the electron delocalization involves all of the carbon atoms, each carbon atom contributes a p orbital to the same pi system. And all the p orbitals are conjugated in a complete ring, and so we say then that this is a cyclic pi system, okay? And those 6 electrons are shifted to convert the first 6 resonance structures into the second, so we can see that the pi system contains 6 pi electrons. Now, the delocalization of electrons around the entire ring of benzene has important consequences. The molecule is highly symmetric. It's also entirely planar. And all 6 of those carbon-carbon bonds are equivalent. Right? And then, more importantly, from a chemical standpoint, benzene's system of pi electrons are unusually I think it is here, working on my subject-verb agreement, is unusually stable, right? And so because we have this aromaticity, because this is what we consider aromatic, it's very, very stable. You can gain a rough feel for how stable benzene is by comparing these 2 equations here. In equation 1412, bromine is going to add across the double bond in a reaction that we learned about in chapter 13, okay? But if we look here at benzene, there's no reaction that occurs under the same condition because those 3 double bonds that make up the pi system would have to be, that would disrupt the aromaticity for this to undergo a reaction. And so benzene's just too stable to do that because of that aromaticity. So what that means is that benzene undergoes a substitution reaction rather than an addition reaction. And this can be explained in part by the resonance delocalization of pi structures. When we talk about this, the resonance structures are equivalent. And so when this gets substituted for one of the hydrogens, the benzene ring's pi stability is maintained, or the aromaticity here is maintained. And so that's why this reaction is particularly favorable. Now, resonance doesn't fully explain benzene stability. If it did, then we would expect a similar stability in the pi system of cyclobutadiene. Just like benzene, cyclobutadiene's ring consists of alternating double and single bonds. However, cyclobutadiene's pi system is really, really unstable. It's so unstable that the compound's only been isolated and studied in an argon matrix at really, really low temperatures. Moreover, what we've seen is that when people have studied the bond lengths of cyclobutadiene, there's 2 different carbon-carbon bonds. One that's consistent with a carbon-carbon double bond and one that's consistent with a carbon-carbon single bond. And remember, all of benzene's carbon double bonds and single bonds are actually the same length because of the electrons are delocalized. So what this means for us is cyclobutadiene doesn't exist as a symmetric resonance hybrid like benzene does, but it equilibrates between 2 different structures. So what does this mean for us? Well, benzene and cyclobutadiene are members of 2 separate classes of compounds, and these 2 different classes of compounds exhibit different characteristic behavior. Benzene is going to be classified as aromatic, and cyclobutadiene is classified as anti-aromatic. So aromatic compounds generally have cyclic pi systems that are unusually stable, and anti-aromatic compounds have cyclic pi systems. And aromatic compounds, let me just start over. Aromatic compounds have cyclic pi systems that are very stable, and anti-aromatic compounds have cyclic pi systems that are very unstable. All other compounds are classified as non-aromatic, and that means they're not unusually stable or unusually unstable. There are a variety of other aromatic compounds and aromatic and anti-aromatic species besides benzene and cyclobutadiene that we've looked at. And so the burning question in your heart is, well, how can we identify if a species is aromatic, anti-aromatic, or non-aromatic? And of course, I'm so glad you answered that question or asked that question, and it will be answered in the very next screencast.